of this conference for giving me the opportunity to share some of our research work with the young students. I see a good number of young students sitting here in the hall. So, my topic of today's talk is the facile synthesis of Azaphospha Heterocycles from functionalized Cycloiminium Ylides and related imines. So looking at the audience, the students are here. I will emphasize more in my talk on the type of heterocycles. Like if you are studying chemistry as one of your major subjects at the undergraduate level, you are already aware about the heterocyclic compound, and we talk about the synthesis of that. So during last few years, we have done some research work on phosphorus heterocycles. As we know, whenever we talk about heterocycles, our undergraduate students, what do you think? A heterocycle is a compound having nitrogen, sulfur, oxygen mainly. Okay. So now I am talking about the phosphorus heterocycles. So when I say phosphorus heterocycles, earlierly the phosphorus heterocycles were used to be in the inorganic chemistry. The phosphazenes, the phosphobenzene was studied in inorganic chemistry, but now during the last couple of decades, the carbon phosphorus analogy. So there is a book, The Rise of New Domain by F. Marthi, Phosphorus Carbon Heterocyclic Chemistry. So it has given the phosphorus heterocycles the equal status in the heterocyclic chemistry, the heterocyclic compounds, as nitrogen, sulfur or oxygen heterocycles. So the phosphorus heterocycles, for the benefit of the students, I would like to give a brief introduction. Depending on the size of ring, the phosphorus heterocycles can be categorized into different categories. If we start with the 3-membered ring with one phosphorus, the compounds are phosphetranes, then unsaturated phosphirenes, then 2 phosphorus, diphosphidanes. So likewise the nomenclature goes on as is for the nitrogen heterocycles. Then 4-membered rings, these all heterocycles are available with us. They have been synthesized in the laboratory and their properties have been studied. So 4-membered ring with the phosphorus is phosphetane if it is saturated. If it has unsaturation, dihydrodiphosphates. And 5-membered heterocycles are important because we study the 5-membered heterocycles first, like pyrrole, purane. So here we have the 5-membered ring with phosphorus. If it is saturated, the compounds are phospholane. If one double bond is there, the compound is phospholine because of the unsaturation. And then this is similar to the pyrrole. So this is phosphol, analog of pyrrole. And then we have here this category of compound where apart from one phosphorus, there is another heteroatom X in the ring, the 5-membered ring. And these compounds are called heterophosphols because in addition to phosphorus, we have another heteroatom. Then 6-membered phosphorus heterocycles. So this is analog of benzene. So this is called phosphobenzene or phosphenene. So here you can see this is lambda 3 phosphenene, and here we have another category of compounds, lambda 5 phosphenene. So because the phosphorus has resemblance with nitrogen and some difference also, the phosphorus forms PCl3 and PCl5. The nitrogen can form only 3 coordinated compound. So similarly here, because of that property, the phosphenenes are of 2 categories, lambda 3, the 3 valency, and lambda 5. Similar to quinoline, the phosphoanalog are called phosphenolene. So then we have, because of the lone pair available on the phosphorus, some other categories of phosphorus heterocycles, phosphenene oxides and sulfides, dihydrophosphenene, and then some other complexes where the lone pair available on this phosphorus, which is not available in the pyridine, similar to here the phosphorus has this lone pair which can be donated for the complexes, so sigma complexes are there. So then there are also available which can come under the category of macro cyclic compounds, polycyclic compounds and spiroheterocycles. The phosphorus can be present at the ring junction of the two rings. And in spiro compound is a compound where two rings they are joined at one common atom. So why we are interested in phosphorus heterocycles? Because of their application in the phosphorus heterocycles in homogeneous catalysis, in the coordination chemistry, molecular materials and biochemistry. So phosphorus is a very essential material in our biological system. So we are interested in the phosphorus heterocycles. My interest is in the aromatic phosphorus heterocycles, and these two categories they come under the aromatic categories. Here we see this is an analog of benzene, and the second one is the 5-membered heterocycle having aromatic ring. The phosphorus a member of aromatic ring. And the compounds what we have synthesized they come under these two categories, where a 5-membered ring having a phosphorus is annihilated with another ring. Here I have shown this as a circle. This circle can be a pyridine ring, pyrazine ring, it can be thiazolene, thiazole, quinoline, isoquinoline. A large number of other ring systems are annihilated to this 5-membered ring. A nitrogen and a phosphorus they are essential. Apart from that, some other heteroatom positions are also possible. Here, if there is a pyridine ring, we see that nitrogen is at the bridgehead. And this is another category of azaphosphore we can call it, because of the 5-membered ring. The name comes phosphore because of the presence of one nitrogen azaphosphore, and here this is annihilated to one benzene ring. So we see that a large number of phosphorus heterocycle categories are available. So my interest was the synthesis of phosphorus heterocycles. We started with a very simple method for the synthesis. Here salts, iminium salts. We know the pyridine or any nitrogen heterocycle, because of the availability of lone pair, the nitrogen undergoes quaternization. So if there is active hydrogens present at the two positions at the carbon neighboring to this nitrogen, we have a 4-membered chain. We react it with the phosphorus trichloride and the condensation takes place and 5-membered phosphorus heterocycles are formed. So during the next few slides I will be showing how the intermediates, the starting materials, they decide what type of product is going to be formed, and how we can use in today's world the computational calculations they are being used to rationalize the synthetic results. Whenever you think that you mix two reactants in the laboratory and a third compound will be formed, but you observe that what you thought this has not formed, you get some different product. So why some different product has been formed? Okay, so we can nowadays take help of the computational calculations and can justify by optimizing the intermediates of a reaction that which intermediate has to be formed and that decides which product will be formed. So all this work has been published in the form of research papers and in the form of book chapters in this is a series topics in heterocyclic chemistry, where we have 2 volumes of phosphorus heterocycles. There is one chapter dealing with this compound. So now I come to the synthesis from the cycloiminium ylides and imines. Ylides are the compounds, the students we know, where the carbon is having a negative charge and it is attached to an atom that is positively charged. This is normally a heteroatom. So such type of compounds are called ylides. So the pyridinium ylides, when you have a pyridinium salt, you treat it with a base, the proton goes with this base abstracts the proton from here and an ylide is formed. If you treat this ylide with phosphorus trichloride, dichlorophosphorylation takes place at this carbon. And these compounds are very versatile intermediates for the synthesis of phosphorus compounds. So here, if you have a substituent having CH2 group at this position, you have one 2, 3, 4 and 5 membered chain. This 5 membered chain undergoes cyclocondensation. We know the condensation reaction, and if the product is cyclic, you get this type of compound, the heterocyclic compound. We call it phosphoindolysine, because if this phosphorus is not present here, the heterocyclic compound is known as indolysine. And if we introduce phosphorus here, and this is the 2 position, because the numbering starts from here. This is 1, 2, 3, nitrogen is 4, 5, 6, like that. So at 2 position phosphorus is there, so the compounds are called 2-phosphoindolysines. So the phospho analogues of indolysines have been formed. So now if you have a CH2 group here, the reaction is cyclocondensation reaction. But if you have no substituent at this position, if R2 is hydrogen, then there is only a 4-membered chain. But this undergoes disproportionation and then undergoes 1,5 electrocyclization. If there are PG students sitting here, they have studied the pericyclic reactions, and in the pericyclic reaction 1,5 electrocyclization undergoes the pericyclic reaction and this compound is formed. So these 2 compounds, they look similar, but there is a basic difference. Here there is one electron withdrawing substituent, ester group, at this 3 position, and here at this position we have alkyl substituent. In the second type of compounds, we have the electron withdrawing substituent, the ester group, both at 1 position and at 3 position. So in such type of compounds, what is the difference? The difference is in their reactivity. You know, these are the aromatic compounds like indolysine, quinoline, isoquinoline. They are aromatic. The double bonds are conjugated. But here in these compounds, they are aromatic, but there is a difference. They are 10 pi electron system, but there is a difference that this CP double bond is susceptible to cycloaddition reactions. So these are the reaction type of reaction can take place at this bond, but only when we have this electron withdrawing substituent at both ends. So these compounds, they undergo cycloaddition reaction, and these compounds, they do not go facile. These are the reaction. So now I come to the mechanism part of the synthesis of these compounds. So like here, if you take alkyl substituents at 2 ends, here you have R1 an alkyl group and R2 an electron withdrawing substituent. There can be another substituent in the ring at any other position. So the cyclocondensation, we call it 4 plus 1 cyclocondensation route because of the 4-membered chain reacting with the phosphorus, the 1-membered part, and these compounds are formed. The structures have been verified by the X-ray crystallography. So this route involves as I told you earlier, this Ylide intermediate, the initial formation of this Ylide, which reacts with PCl3 to form this dichlorophosphanylated Ylide, which undergoes cyclocondensation. So we could isolate this Ylide, the intermediate, and its structure. Its structure was verified. There were some interesting features, like you have one PCl2 group. When we have this PCl2 group, there are 2 PCl bonds, and here we see that the bond length is very much different. One bond is only 206 picometer and the second one is 270. So there is a great difference between the 2 bond lengths. Why the bond lengths are different? We have investigated it with computational chemistry. So I will come to it after 2-3 slides so that you can see how computational chemistry can help us in understanding the principles of synthetic chemistry. So here, like in this slide, we see there is one electron withdrawing substituent here. The reaction is initiated at this carbon and an Ylide is a product, intermediate. If you don't have an electron withdrawing substituent here, if you have a phenyl ring that is not so much electron electron withdrawing, the reaction is initiated at this carbon, not at this carbon, and a different type of intermediate is formed. And this different type of intermediate can be identified by the phosphorus NMR spectroscopy or the carbon-13 NMR spectroscopy, which shows the presence of two PCl2 groups at the carbon. And here again the cyclocondensation reaction gives you the phosphine doping. Then, if you don't have a substituent at this position, here you have hydrogen, here you have hydrogen at the carbon adjacent to this nitrogen. So here you see that this intermediate Ylides disproportionates into another compound which are called Ylides, because here you see this part is similar to an Ylide, phospholipid group. Okay, so it again undergoes 1,5 electrocyclization and you get again a similar type of heterocycle having electron withdrawing substituent at the both sides of the phosphorus. Okay, so until here we have seen that if we have electron withdrawing substituent here, the reaction starts here, and if you don't have electron withdrawing substituent here, the reaction is initiated at this carbon. So why this difference in the reactivity? So how can you justify it? We investigated this type of orbital. Those students who have seen the sigma and sigma star orbitals, they can identify that this shape, these four balls, blue, and red, they indicate sigma star orbital. If you can understand, what is the shape of sigma orbital? Normally we show sigma orbital like in the center, when we have two carbons, in the center we have one lobe having one charge, suppose plus, and on the two ends we have small lobes with minus. Okay, and if we draw sigma star orbital, it is something like that. In the center is the node, on one side is this plus minus and then plus minus. Okay, so here this is the orbital on the carbon. The extra electron on the carbon is in the pz orbital, and this pz orbital is in the same plane to the sigma star orbital, and it can donate, they overlap. You can see this anti-bonding orbital and here this orbital, they are overlapping. Since they are overlapping, the electronic charge is donated from this orbital to this orbital, and any donation of charge from one orbital to second orbital leads to delocalization, and this type of delocalization is known as hyperconjugation. And any type of delocalization, hyperconjugation, it leads to extra stability, and because of this hyperconjugation, the molecule having two different bond lengths, because here only one PCl bond can be in a plane of this pz orbital. The second PCl bond is not in the plane where the electron can be transferred, so one bond is longer. Which one is longer? Which one is longer? The sigma star orbital has got electrons, so the anti-bonding orbital has electrons, the bond order will decrease, the bond length will increase. So because of the hyperconjugation, this PCl bond length is longer. So here you can see, because of the presence of this chlorine, this hyperconjugation is taking place. If you replace this chlorine by hydrogen, here, if you replace it by hydrogen and again calculate the molecular orbitals and visualize them, here you can see the orbital on the phosphorus and the orbital on the carbon, they are orthogonal to each other, perpendicular to each other, and when two orbitals are perpendicular to each other, the electron cannot come from one orbital to another orbital. So here you can see that the extra stability can take place if there is a possibility of delocalization of this charge into these two groups. So if this electron is able to go into the antibonding orbital of this carbonyl group and this PCl bond, so this electron does not go for delocalization into the pyridine ring and the geometry is perpendicular. But if you replace one of the groups with hydrogen like here or like here, in both of these two geometries, now this negative electron electron is not able to be delocalized into these groups. Now it goes for stabilization into the pyridine ring, and you have these two types of geometries. Here the pyridine ring and the elliptic carbon plane, they are same, and here also they are same. If you add one hydrogen here, now the charge is not there. You can see the elliptic charge is not here because the carbon has 4 valencies. So here again this pyridine ring and this PCl2 bond lengths, you can see now these two PCl bond lengths are same. So the two PCl bond lengths, they become unequal because of the phenomenon of hyperconjugation. So then, with the help of computational calculation, some more phenomena have been investigated. Here you can see 1,5 electrocyclization versus 1,5 proton shift. So these all are the topics of pericyclic chemistry. The students who have studied pericyclic chemistry, they can identify that how the intermediates are formed and the shifts can take place, and we can study all these mechanisms, all these intermediates with the help of computational chemistry. So these heterocycles are very interesting because they show wide variety of reactivity. Because of the presence of this hydrogen at the carbon adjacent to phosphorus, electrophilic substitution reactions can take place. Then, because of the presence of this CP double bond, which makes these compounds aromatic but not as aromatic as the carbon analogues, 1,2 addition reactions take place. They can undergo 1,2 addition as well as 4+2 cycloaddition. Then because of the presence of lone pair of electron at this phosphorus, 1,4 cycloaddition, oxidation and coordination reactions can take place on these phosphorus atoms, and a variety of reactivity of these compounds can be investigated. So how much time do I have? Over, I think. So I will skip next slides because they deal with the computational calculations of the reaction mechanism. Here you can see with the help of calculations we can investigate where this metal coordination takes place. So the computational calculations can help us in understanding which intermediate will be formed and which product will be formed. You can calculate the energy of activation, you can calculate the energy of reaction to find out. So these are some more phosphorus heterocycles. They are interesting. Here you can see this phosphorus is in hexa coordinate state. The phosphorus is at the bridgehead of 4 rings. So these interesting phosphorus heterocycles can be synthesized in the laboratory. So I acknowledge my research scholars. They are all my research scholars who have done the above research work, and the financial support from the DSC is acknowledged.